Selective laser sintering, abbreviated as SLS. We can see here, number 1 is the leveling roller. Number 2 is the powder feed supply. Then number 3 is your powder bed. Number 4 is the powder feed. Number 4 is the, let's delete this. Number 4 is the powder feed piston. Number 5 is the belt piston. So powder feed piston, it goes up to be able to supply the roller with a new powder to push it to the right, to the belt area. So number 5 is the belt piston. This piston will go down each time the layer is formed to be able to form the final object. Number 6 in here is, it's not showing in this picture. Number 6 is the belt chamber, which should be down here. Then number 7 is the centered part. Number 8 is the laser beam. Number 9 is the XY scanning mirror. Number 10 is the lens where the laser pass through. Number 11 is the laser source. So summary of the selective laser sintering process: laser goes through lenses, then reflected through the XY scanning mirror, goes down to the belt powder through a certain pattern based on the actual design order being sent to the 3D printer. When the layer is finished, the belt piston will go down in the thickness of that layer to be able to receive a new layer. And the bed, when the powder feed piston will push up some powder, and the feed roller or leveling roller will push more powder to the building area to be able to sinter more material to produce that 3D part. Now this SLS method uses powder container of small particles. These particles can be fused by laser to be solidified and create the final object. The laser being used is a highly powered. It follows a certain trace that is programmed for each layer according to the CAD data, as we mentioned before. This is another illustration of the SLS process. Again, you have the laser, goes through the lens, it reflects on the building bed, which is full of the needed powder. It follows a certain pattern, and each area the laser passes through moves from the powder state into a solid state. When the layer is finished, the bed will be moved down in the thickness of that layer so that it will be ready to a new layer. This feeder will push more powder supported by this Y feeding layer, Y feeding powder piston. Then the roller feeder or leveler will push more powder in and level the powder to be even and straight to receive the laser, and so on until your part will be finished. Then you clean your powder and the part will be ready to go. A close up on the material being exposed to the laser. You can see here, this is the powder that need to be moved from a solid state from a powder state into liquid, then eventually will solidify and become in solid state in a certain pattern to be able to create your final product needed. Looking at the powder used in the selective laser sintering, we can see here the gray and black dotted circles are solid, which means a particle non-melted core or coating. Then the white circle is the liquid or the melt. It's a kind in a liquid state. So in A, we can find here, this is a single component metal powder. You can see how it's getting melted from the outside and being connected to the next grain of powder as a one piece. Then in B, you can see two component metal or metal powder mixture. So we have two components of metal, but we have a powder in between that's not melted yet. Then we can see here through the process how the formation of these metal powders or grains, they change their formation during the laser sintering. C, we can see two components of metal or metal coated powder. We can see here the particle is the solid and in a particle state, non-melted core or coating. Then it just changes as being exposed to laser. As we can see under the microscope on the left, this is the raw nickel alloy copper powder mixture, and here we can see raw steel copper powder mixture. Now after sintering, we can see the metal copper powder mixture. After sintering, it will be looking this way. So as we can observe, the particles are not separated anymore. They are homogeneous, one like in one part, and stick to each other as a solid part. If we move next, the plaster based 3D printing, you basically, this kind of method of 3D printing, you have a printer that's having inkjet inside of it, and you have the printed part in here, you have the leveling roller in here, and you have the powder feed supply. So this kind of method use a bed of plaster particles instead of the powder particles. Then the print head extrudes the liquid adhesive to stick each plaster particle to the next one, and it doesn't require any supporting structure because the part is lying inside these plaster particles container, and it requires some post-processing because the resolution of the final part is not perfect in most cases. Then if we go next to the granular printing techniques, so this technique, bending the granules with bonding material like glue, and it can as well sinters the powder by heating them below their melting point, and it can be by melting as well. So granular printing can be done by melting, combining powders by heating them above their melting point. Then you create a full melt pool of material, and that's done using laser or electron beam to provide the energy necessary to fuse the powder where the final product need to be. If we talk about the granule solidification method, basically the granular powder technique used for plastics, metals, ceramic printings, it is made to create large 3D printed projects or objects. There's several existing ways to solidify the granules, and you can basically change their state from powder to solid objects through several ways. So if we talk about the laser powder sintering, basically, as we can see here, we talked about this process of laser sintering. The laser projected on the powder pool and creates layer by layer by melting the powder into liquid. Then it will solidify to create the final solid object. If we look into the right here, there is the laser beam and there's the laser sintering happening in here. Then we can see here pre-placed powder bed. That bed is supporting these particles, and you can see here the unsintered material in the previous layer still in here, and as the laser is scanning these particles, they are solidifying, becoming liquid, and one part then getting solidified based on the laser mapping that's been done related to the object dimensions. If we talk about the binding powder, so the powder binding printers, they use the inkjet sprays. So they apply a rapidly solidified binder into a powder bed. Then they create a solid objects from this sprayed glue to the base powder of the material. So you can see down here, you have your powder roller. It pushes the powder in here. Then this is the part that's newly generated, layer by layer. Green parts means a part that's newly sintered and still solidifying. And this is the bound powder. Then here you have the binder spray head that is binding, binder spray head that's binding each powder particle to the next one. And then you have your CNC operation nozzle. And this is the liquid binder in here, moving X and Y directions as needed and based on the printer design. Again, this is the build tank. Every time you make a layer, the build tank will move in the thickness of that layer until you create your final product. So when you create the entire model, then the unused powder is removed from the part so that you can reuse it later. And if your final object is bigger than what the printer can print, it's bigger than the space of the printing bed, then in this case you can make your assembly as a part, like as a couple of group of separated parts that can be combined together later, as we can see here in this picture. So these components are printed, then eventually they are combined together as an assembly. So basically you can, there's many ways, as we will learn through this process. The 3D printing can create interlocking features so that you can assemble each component with the next one instead of making a big one chunk of assembly. This will save you the effort in comparison to the regular manufacturing process that we know. And the plastic powder objects, they remain granular and they can be crushed and they don't have any kind of big strength until you dip it in resin so that you can fill the spaces between each of granules, so that the empty space will be filled with resin that will give it more strength and durability so that it can be conveniently used without getting broken. But in case of metals and glass casting, then the solid shapes, they are getting stabilized by exposing them to heat so that you can fuse the binder and the powder together. But if you're using like simple metal powder to infuse the powder binder mixture, you can add additional liquid metals like bronze so that you create a stronger alloy and a more acceptable appearance for the material. So the powder bed supports the solidified bound material, and that is helping in the production case. That helps you create a large and complex design without needing like lighter elements or needing a supporting planning for that part, and that will help the part not to break during the making of the object or during fabrication. Some powder beds are used to support so that it will help continuous creation of objects. They are using a binding jets that operate across a tilted granule bed, and then there is a conveyor belt. It moves the entire volume of powder slowly through the printer. So in this case, the printer builds models by just adding more powder layer over layer along the inclined and selective binding the powder. Then according to the 3D design, you will be following the mapping of the 3D design over the powder to create your final product. And this kind of property You can use it to fabricate solid objects that are maybe longer or bigger than the entire printer depth, and you can even print the front end of the model, and the rear extends beyond the conveyor behind the printer, as we can see in the graph. For the blown powder method, this method, they basically work by blowing the metal powder into a laser or electron beam. So adding the blowing powder to the melt pool that is formed by the heat source. This method can be useful when the material required very high level of heat to be able to melt, same as the material examples like tantalum and titanium. And mostly these materials are used in aircraft manufacturing applications, and as well the edge cladding of turbine blades. Either is it for repair or enhanced operation, so this kind of technique can be used in these applications. So blown powder, it can be applied for any complex part, and you don't need any other efforts. Similar to any other 3D printing, you just design your part, either complex or simple, and you just send your printing order, then you get your part. The good about it, it can give you even more complex parts with the same amount of processing time. For the lamination processes, so instead of having like layers of powders or melting materials, in this case you are having just laminated cuts for individual layers of material. Then you combine them together through a glue or a combining material, and these materials could be metal foils, could be plastic sheets, or even common papers that can be used to create laminated objects. If we can look into the process of laminating the object manufacturing, which is abbreviated as LOM. So you have your laser in here, then you have the mirror, optical head. This head, same as the XY mirror we mentioned before to project the laser, it goes through a certain map related to the 3D design that we provided to the material. Then on these rollers you have a material coming in, and this is the material, could be either metal foil or a kind of paper that you need it to be used as a material for the created objects. Then you cut the needed layer and you provide a new material. Then the laser will cut the next layer and put a glue through this rolling bed, and so on until you create your final 3D objects. So the final product is not very strong. It's basically as strong as the material you used, either paper, foil, plastic. Then don't expect a high strength or durability for that part. It's just used as a laminated object. And the problem of this kind of method, it lacks the resolution in the z-axis. So because each layer you cut, then you put some glue, create a new layer. So each layer can't be taller than the thickness of the sheet. So in this case, you have a kind of differences in the thickness between each layer and the next one, and that reduces the resolution along the z-axis. If we talk about the fused deposition modeling, abbreviated as FDM, it is one of the best known additive manufacturing techniques and one of the famous ones. It's invented in 1980s. It used the STL files created by the CAD 3D design softwares. And the fused deposition modeling, it squeezes the melted thermoplastic through a small nozzle to create an object. It's as simple as that. We can see in this graph, so you can imagine it as the toothpaste. You push it, it will put the paste out, then you can lay it down on the sheet in the way you want it to meet the final the design of the product that you have. And then you can move the base up and down and the nozzle up and down as needed in order to identify the point where you want to deposit the paste in the space. The paste in this case is the melted plastic. So these plastics getting cooled with time to room temperature in minutes, then it will be a solid objects that can be used. Fused deposition modeling is known as well as the fused filament fabrication. So let's remember that FDM is same as 3F, which is the fused filament fabrication, same as fused deposition modeling, same naming for the same process. And for this process, the thermoplastic materials used, they are usually sold in big containers for thin filaments. They are different in width, between 1.75 up to 3 millimeters. They are either made out of ABS material, polymer, or even polylactic acid, which is known as PLA, or PVA for support, nylon, and composite materials. So the cases where used the wood or plastic composite filaments, they are usually sanded and painted like woods, and they give even a grain-like pattern, which can give it more aesthetic feeling than the regular ABS, PLA, PVA material. But all of them are thermoplastic that solidify through time and give you the final product needed. 3D printers, they usually require the use of cartridges that are loaded with the high quality filament, so that the filament is produced in the thickness needed, and this filament can be melted on the precise temperature needed, so that there will not be any troubles in the nozzle or clogging due to the insufficient temperature or solidifying through the nozzle. And this way, when you get a high quality filament, then your printing will be easy, but as well it will cost you, where the cartridges can be expensive.